Another cool fact, the colder and older the rocks are, the further seismic waves are going to travel. I'm Danielle Fougere, and I'm an earth scientist at the University of Southern California. I'm here today to answer your paleoseismology questions on Reddit. This is RUBICON on Reddit. Wayne Almighty asks, what is a fault and how does it cause earthquakes? I tried looking it up on Wikipedia, but I'm still confused. Thanks in advance. So, a fault, very simple, is just a zone of weakness where two blocks on either side of the fault move relative to one another, and when they do that, causes an earthquake. So, the Earth's surface is made up of a bunch of tectonic plates. Those move around and interact with one another. And where those plates interact with one another are called plate boundaries. And faults are the structures within plate boundaries that accommodate those motions of the tectonic plates. Oh, yay, I love this question. Okay. Bubble, R-E-T-A-R-D asks, why does the mountain range in SoCal split like this so geometrically? It almost looks like it was pulled laterally east and west. Guess what? It was. There's a little triangle shape you can see drawn between the San Andreas Fault and the Tehachapi Mountains. This is the westernmost corner of the Mojave Desert. And this is the spot where the Garlock Fault, which is a fault that runs east-west, intersects with the San Andreas Fault. So the reason why there are these very linear mountain features that don't really look natural is because there are faults there that are interacting with one another in a very complex way to either uplift some of these mountains, to pull the Mojave Desert eastwards. There's all sorts of different factors in this area, but yes, this incredible topography is formed by these strike-slip faults and them interacting with one another. Mesa is the Senate asks, if an earthquake is a giant plate moving, why is the epicenter a single point and not the entire fault line? An earthquake is caused by two blocks rubbing against one another, causing friction and releasing seismic waves. At the nucleus, the point at which that earthquake rupture starts in the Earth, that's called the hypocenter. If you take the hypocenter and you draw a straight line vertically up to the surface, that is the epicenter. The actual earthquake ruptures along 2D space, along the fault plane, and so the word epicenter is actually just used to describe the point on the surface at which that earthquake started nucleating from. Iron Landscape asked, I just read a post where it was explained that in 1600-ish, there was the strongest earthquake ever registered with a 9.5 Richter in China. How do we really know it was a 9.5? I mean, it's an estimate because it happened in the 1600s. I'm guessing that geologists have done some paleoseismology. Paleoseismologists can directly look at faults to figure out the age of faults. We can use them to figure out, sometimes used to figure out how big the earthquake was, and also the amount of damage recorded is a good indication if you know what the site looks like, so what the ground looks like beneath your feet. But yeah, different lines of evidence. MZ Incognito asks, in my Intro to Earth Science course, I learned that the Pacific Plate is moving relatively rapidly to the northwest. Why is the Pacific Plate going in that direction? So the Pacific Plate is a pretty big plate. On a lot of the edges of that are called subduction zones. So the Pacific Plate is subducting beneath the other plates around it. And that subduction is kind of pulling the plate towards the northwest. It's controlled a lot by those plate boundaries where the plates are interacting with each other. A lot of them are coming towards each other, convergent boundaries. Some are transform boundaries, but yeah, they help to kind of pull that plate in specific directions. Renato727 asks, tectonicism is divided into two categories, orogenetic movements and epirogenetic movements. But this classification seems to overlook some effects on the relief. Typically, how tectonicism is taught in terms of plate boundaries is that there are three types of plate boundaries: convergent, divergent, and transform. And those are just different ways to describe how the plates are moving. Convergent, the plates are coming together. An example of this is the Himalaya, big mountain range formed by two plates colliding and one subducting beneath the other. There's divergent, where the two plates pull apart from each other. These areas are where new crust is formed. So these plates pull apart, so magma comes up from the inside of the earth and cools and forms new crust. These boundaries typically are seen in the middle of the ocean, so mid-ocean ridges. If you look at a satellite map, you will see, kind of looks like the seam of like a baseball running through the ocean. Those are divergent plate boundaries. And then there are transform faults. So an example of a transform fault we all might know is the San Andreas Fault, where two blocks of Earth are moving relative horizontally to one another. So we have convergent, divergent, transform, and these three types of ways plates interact with one another help to accommodate all these different motions that are happening. AETHELREDIS Ready asks, what exactly is striking and slipping at a fault near but not on a plate boundary? I don't really understand what is happening at the Hayward Fault. This is an awesome question because plate boundaries and faults are very confusing. However, plate boundaries can be discrete and linear and be on one fault, or it can be distributed across multiple faults. So the Hayward Fault up in Northern California is one fault in the San Andreas Fault system that accommodates motion between the Pacific Plate and the American Plate, the North American Plate. When you think of a plate boundary, you probably think just one discrete line, but in reality, this is not what usually happens. There are places around the world that do. For example, the Alpine Fault that runs through the South Island of New Zealand is a pretty linear plate boundary. In Southern California, where I live, the plate boundary is really complex. The San Andreas has a big bend in it. We have what's called the Eastern California Shear Zone, east of Los Angeles or northeast of Los Angeles, and that structure, the Eastern California Shear Zone, made up of a bunch of faults, and the San Andreas Fault both accommodate plate boundary motion in Southern California. So it gets very confusing. So TyTheBuy14 asks, what happens to an intraplate fault when an earthquake occurs? So I've been talking about faults at plate boundaries that are accommodating motions between these plates. However, there can be faults within the plates called intraplate faults, and these can be formed from many different reasons. One of those being, its geologic history. So for example, in the Midwest in 1811, 1812, there were some really big earthquakes that caused a lot of damage. And this was the New Madrid, what's now called the New Madrid Fault Zone. And this area is not typically one that experiences earthquakes because it's not on a plate boundary. However, back millions of years ago, it was a plate boundary, or it was trying to be a plate boundary. So there was a zone of weakness kind of formed during that time. Geologic time has progressed. However, and that area is not on a plate boundary anymore. However, that zone of weakness still exists. And over long periods of time, the fault can still accumulate strain energy from that big plate moving. Another cool fact, the colder and older the rocks are, the further seismic waves are going to travel. So on the East Coast, if there's an earthquake, typically it's felt along across a larger distance because the rocks in the eastern US are colder and older than those in the West. So just a cool little fact. Sharp Pomegranate 121 asks, why is part of Southern California's landmass on the western side of the fault, and why doesn't it run closer to the coast? So I think this question is asking about the San Andreas Fault and why the coastline is not coincident with it. And this is because faults don't necessarily control where coastlines are. They can if they uplift or cause subsidence of the earth. However, the location of the coastline is mostly determined by sea level change. So climate change can affect where the coastline is, and also, subsidence and uplift of the land itself caused by faults often. Brave Ad 5326 asks, would a strike slip cause a tsunami the size of the one that hammered Japan in 2011? The answer is no. The reason why the Japan earthquake and tsunami in 2011 was so big is that it was a subduction earthquake. And because it was a subduction earthquake, that allowed for more area of the fault to rupture. And because the fact it slipped all the way up to basically the sea floor, it caused a block to drop down a lot. And the water on top of that also dropped down, and that's how that big wave was created. Strike slip faults like the San Andreas Fault move horizontally and don't have the ability to displace all of that water. However, earthquakes on land can potentially cause tsunamis if they trigger a submarine landslide that may displace water that could cause a tsunami. But in Los Angeles, we're okay. We're okay. So Earth Love asks, what location on Earth is the core measured from? How is the central core found? How do scientists know the liquid detected in the P waves isn't just some ocean? The way scientists were able to figure out the different layers of the Earth and study them is largely to do with recording seismic waves from big earthquakes that happen around the globe and studying how these waves travel through the Earth. Scientists know that these waves travel through materials that have different properties differently, so they're able to determine whether the core is liquid or solid, because specifically S waves, so there's P waves and S waves are the main waves we feel in earthquakes. S waves, secondary waves, shear waves, they do not travel through liquids. So when scientists were looking at these recorded seismic waves, they noticed that there was a S wave shadow within the outer core. B STEM asks, how do we know what the magnitude of earthquakes was before the Richter scale was a thing? The Richter scale wasn't invented until the 1930s. The Richter scale uses the amplitude of the seismic waves released by an earthquake to estimate a magnitude. And a magnitude is a single measurement of the amount of energy released in an earthquake. So the Richter scale was invented. It's also called the local magnitude because it is good at detecting or good at estimating magnitudes that are close by. However, if the amplitudes are too large, it can go off scale. So the Richter scale is actually not as used as much anymore, and we use what's called the moment magnitude scale, and this uses a direct measurement of the amount of energy released based on the area of the fault ruptured. So to estimate magnitudes back before there were records, if we know how long a fault was and how deep earthquakes can rupture, then we can estimate magnitude from that. The postman Pat asks, what did people think was going on during earthquakes when they were not even defined as earthquakes or as a scientific phenomena? I think a lot of people thought it was the work of the gods. I think a lot of people related, these movements to higher beings and whatnot. But Wagamaga asks, the earthquake 3,800 years ago had a magnitude of around 9.5, and the resulting tsunami struck countries as far away as New Zealand, where boulders the size of cars were carried almost a kilometer inland by the waves. I don't see a question here, but this is very interesting. Pacific plate is also around it. It's called the Ring of Fire. There are a lot of subduction zones. There's a lot of volcanic activity. And sometimes when there's a subduction zone earthquake that's big enough to cause a tsunami, that tsunami can travel all the way across the Pacific. It travels about the speed of an airplane traveling across the Pacific. And once it gets closer to land and the depth of the seafloor shallows, that wave can actually gain some height and cause a tsunami. So an earthquake, if it was as big as 9.5, very likely could carry a car-sized boulder inland. Very much so. These things are immensely powerful. Aggravating Major 363 asks, is it possible that earthquakes from fracking could trigger a larger one in the long term? A lot of the large earthquake activity is driven from deeper below, at least that's what I believe. So, you have humans interacting with the rock very close to the surface. I don't think it will cause large earthquakes, but I could be wrong. MC4 Atheists asks, how far are we from predicting earthquakes so that everyone can know well before it happens and takes measures to be safe? I don't think we're ever going to be able to predict earthquakes. There are a lot of people working at forecasting earthquakes. There are a lot of people working on trying to find out the likelihood, the probability of when earthquakes may occur in an area. But there is a serious lack of data because there's a lack of money, a lack of investing into the science, paleoseismology, trying to actually collect data and information from the field. So we are far from predicting. If we could get more money to do some more trenches and collect more data, then we would be much closer to predicting. But for now, probabilistic seismic hazard analysis is our best bet. Two Sheds Jackson asks, if there is significant melting of the ice on Greenland and Antarctica, will this cause a change in behavior of the tectonic plates? Yeah, potentially. This actually is sort of happening now. I think the Laurentide ice sheet that used to cover large parts of North America, when that retreated and melted, the rock that it was sitting under, that was under all this pressure, now has time to rebound. And that's that isostatic rebound can actually cause earthquakes as well, because the earth is moving when it's doing that, trying to readjust. So yeah, very potentially. So Alternative Goat 505 asks, I was wondering what the weirdest question you've ever been asked or the weirdest comment you've ever gotten heard in regards to paleontology. There are no weird questions. Recognition Creative 3 asks, do universities have a department that can analyze an object to see if it is indeed a bone from dinosaur? I have a piece and I would like to see for sure what it is. You can email any professor, grad student, anyone who has is on a department website that's studying dinosaurs, bones, whatever it is, and you can just email them and ask them, hey, I have this bone, I want to know what it is. Scientists love to be nerdy, so when someone approaches us with a question like that, a lot of people are going to jump on the opportunity to help you. Steam Drunk asks, how do paleontologists find fossils with intention rather than finding on accident? Like, how do people find larger fossils? Is it just a bit of guesswork? Yes and no, I believe. You know, as a geologist, we have access, I mean, everyone has access to geologic maps, and those maps contain a lot of information if you know what you're looking for. So those are you can use those as guides, word of mouth. You could certainly stumble upon things by accident. Yeah, I found randomly on a field trip once a penguin bone sticking out of a rock. I found this penguin bone in New Zealand, in the South Island of New Zealand, and I'm forgetting exactly where, but there's also whale bones, shark's teeth, all sorts of things. New Zealand allegedly was underwater at one point during the Oligocene, so we have lots of really cool fossils like that. I have a 2-million-year-old shark's tooth that I was going to bring today and I didn't, but a 2-million-year-old shark's tooth that's sticking out of a rock that found on a field trip in a quarry. So there's just, yeah. Brian Shoup asks, I watched a movie about the flood. Now I have serious geology questions. Is there really no fossil record in the Precambrian layer? Precambrian was, I believe, kind of the first period where there was some life on Earth. This life was very basic, microbes, soft-bodied organisms. To be preserved in the geologic record, soft-bodied organisms are not really the best for that, but there are fossils such as stromatolites that are these layers of microorganisms that can be found around the world that are Precambrian in age. So those are fossils. They're just not your typical bones and teeth that you usually see. And then, you know, soft-bodied organisms are not going to survive millions, billions of years. So they're not going to be recorded in the Precambrian sedimentary layer. But that doesn't mean that there was not life back then. EvenFix7399 asks, during the Carboniferous period, the oxygen levels were so high. I was wondering how oxygen levels stabilized after that. It stabilized over time just naturally. That might seem kind of odd, but during, you know, when we're thinking about these periods of oxygen stabilization, they're happening on millions of year scales. So for it to stabilize, you know, on its own naturally, not because of an outside cause, or specific one that we know of is possible. So, it's just the Earth trying to stay at equilibrium as best as it can. Deep Rough 6794 asks, hi, 18-year-old here wanting to pursue geology as a career. Yes. Do y'all think there will still be places to explore and scout in the US? I know it's kind of a dumb question, but I was really interested in this career. First of all, yes. Geology, please study. It's such a fun field. The demand at the moment for rare earth minerals that we put in electronics and technology, all of that, that's not going to go away. So even though there might be more people getting into that field, the technologies around us are also growing that can help us discover new mineral resources in the US. Those are all the questions today. Thanks for asking such fun and interesting questions.